This is Inverted Lecture 4, and we're going to be discussing how to determine an unknown using mass spec, infrared, and nuclear magnetic resonance data. And I'm just going to talk through some general points on this slide, but there's no one way to go about these problems. So the first 2 points I want to tell you about, and the rest I'm just going to discuss some aspects of, and you'll see when we do the problems together that we may use different information at different times. So first thing, if a molecular formula is given, such as C6H10, determine the IHD, which is the number of unsaturations. If a mass is given, such as 100, then use the rule of 13. And remember that the rule of 13 will give us a formula. So we need a formula for all of these problems, and that does have to be the first thing you do if a formula is not given. Remember that when we talked about the rule of 13, we said you can add in other atoms because the rule of 13 only gives you C and H. So if you have chlorine, you want to subtract 35 right away. Bromine, you want to subtract 79. And for other small atoms, we're going to use CH equivalents. And so oxygen is 16, which is a CH4 group, and nitrogen is 14, which is a CH2 group. And remember that the isotope abundance, where I'm getting these numbers of 14, 16, 35, 79, that chart will be given to you. If you have information from an organic reaction or one is drawn from you, then that at least gives you a hint of what the structures can be because you can solve the reaction. If a direct reaction is not given but parts of a reaction are, remember that you want to take what you can, names of reactions or functional groups present, to help you determine what you have. Okay. Now the rest of these I'm just going to talk through. If you ever have IR data, remember that gives you key functional groups, and you will have IR charts on the exam. For Proton Nmr and Carbon Nmr, you will have chemical shift charts available. APT depth told us the difference between CH2s, those were pointing down, CH and CH3 were pointing up, and quaternary carbons did not show at all. You also want to use information about these to tell how many total hydrogens are in the molecule. This should equal the amount in your formula, and if there's symmetry or not. So if you have 6 carbons in your formula but only 3 peaks in the carbon NMR, then you must have symmetry. Look for peaks that stand out because they're in ranges that are different than others. So an aldehyde H, for instance, is from 9 to 10 ppm, and an H attached to benzene is from 7 to 8 ppm. And again, that knowledge will come from your chemical shift chart. And then from mass spec, we had learned that halogens will have a unique ratio. So chlorine will have a 3-to-1 ratio of the mass and the M+2 peak, and that's due to the chlorine having a 35 isotope and a 37 isotope, and so that's M and M+2 in a 3-to-1 ratio. Bromine, on the other hand, has a 1-to-1 ratio of its 79 and 81 isotope. And remember that M is the molecular ion peak, and so if you're ever given a mass, that's what you're given the mass of, is the molecular ion. Nitrogen, I had forgot to mention this, but it is in your notes, will have an odd numbered mass by mass spec. So for instance, if we have a problem and the mass was 117 AMU, then we would know that molecule must have an odd number of nitrogens. And so it could have 1 nitrogen or 3 nitrogens and so on. In this class, though, we'll consider that it only has 1 nitrogen. And then you should consider what functional groups have 1 nitrogen. So amides, which had a nitrogen with 2 groups connected to a carbonyl, a nitrile, which had a nitrogen with a triple bond to a carbon, and then an amine, which had a nitrogen with 3 single bonds. For oxygen, you're just going to have to give some information. So if you see a carbonyl peak by either C13 or IR, then you'll know that you may have an aldehyde, ketone, ester, or carboxylic acid. And if you don't have a carbonyl group, then you could have an OH, or you can have an ether, or your other two possibilities. Okay, and so we treat these problems like a puzzle, and everyone does a puzzle differently. Do you do the end pieces first or not, or just key parts of that puzzle? That's exactly how we're going to approach these problems. I suggest you pausing as we go through problems and try and solve the part by yourself before I talk through the answer with you. That will make you learn the material better. So the first two problems we're going to do will both have reactions with them, and then the second two problems will be basically an unknown that we're trying to determine the structure. Okay. So for the reaction shown here, we're trying to decide if it's E1, E2, SN1, SN2, or dehydration, and we have to draw the products. So going back to those types of reactions, remember that we needed a alkyl halide as our leaving group, and this is a good leaving group. And then we want to look at our nucleophile, and water is our nucleophile, and this is a poor nucleophile. If you think of the flow chart we did together, that started with the nucleophile on the top, and good nucleophiles were on the left, and poor nucleophiles were on the right. And if we came to the right-hand side, we saw that we had SN1, E1, and dehydration. Remember that dehydration had to have OH as your leaving group. So since chlorine's our leaving group, it must mean that we're going to have SN1 and E1. Both occur, and what problem 2 is asking is how are we going to determine the difference in the products that we can get. So remember, for these mechanisms, they go through the carbocation where the chlorine leaves. I'm not going to draw the whole mechanism, but I am going to draw the carbocation where the chlorine used to be. And that is a tertiary carbocation, so it will not rearrange. So at this point, it can form E1 or SN1 products. And so for E1, we're looking at the beta hydrogens, and we have beta hydrogens at these two carbons in here. So we can get the alkene on the outside or the inside. So that's the alkene on the outside. This is the alkene on the inside. This one is di-substituted, and this one is tetra-substituted, so this would be the Hoffman, and this would be the Zaitsev. And then the SN1 product would be the nucleophile just attacking where the carbocation was. And since our nucleophile is water, our product is going to be an alcohol. Okay, so we have two E1 products and one SN1 product. And we have to go through each of these and determine how we can tell the difference between these products. So let's first start with mass spec. Could we tell the difference of these in mass spec? So what we have to do is figure out the formula of each and then how much each weighs. You can take the time to do that, but I think you can see that an alcohol is going to weigh something different than the alkene will be. So these two are just constitutional isomers, and constitutional isomers just differ in how they're connected, but they have the same formula. So these are going to have the same mass, these two here, and we're not going to be able to tell those two apart, but we should be able to tell the alcohol apart. Okay, so mass spec could do that for us. IR. What key peaks would allow you to distinguish alkenes from an alcohol? So let's start with the alcohol because that's the easiest. And so here's a place where you might want to pause, right? Because I'm going to tell you how to distinguish, and it would be best if you try that on your own first. So I will just say pause when I think it's a good time for you to pause. And we probably should have paused up here as well to make sure that you could draw those products on your own. Okay, so for IR, alcohol would be the OH peak, and remember that was around 3,200 wave numbers, and it was broad. And alkenes have two signature peaks. They have the C double bond C peak, which is around 1650 centimeters inverse, and it's a fairly weak signal. And then we have CH, So remember that the carbon's sp2, so a CH here on this one would help us to distinguish this one. So that would be at 3100 centimeters for compound 1. And compound 2 would have no CH on the alkene. So IR may let us distinguish between these two. And then for NMR, let's also use that example. If this has CHs on this alkene and none here, we will see the CH at the shift region of 5 to 6 ppm. If you have your chart, that's where an alkene is. And this will have no CH peak. And then this will have a OH peak, which is at variable positions. It can be anywhere from 2 to 5 ppm. So IR is probably a better way to tell this compound than NMR. Although for NMR this peak does tend to be broad as well and may be easy to see. Okay, so that's the first problem, where before you could have drawn the reaction, and now we're seeing how to use data to exactly tell what our what our different components of our mixture is. All right, so the next problem, we also have a reaction. It says the reaction below is favored for one specific regioisomer. Draw that product and then draw the other regioisomer as well. So let me just quickly remind you what regioisomer is. If we have an alkene, remember that a reagent can add to an alkene this way, such that X is on this outside carbon and Y is on the inside carbon. Or it can be reversed. Y is on the outside carbon, X is on the inside. This is what it means to be regioisomers. And so if we look at this problem here and we see our alkene is going to react with HBr and ROOR is peroxides. Then the H can add on the outside carbon and the bromine on the inside, or the reverse. So let's draw both of those. So there's bromine on the inside and I just didn't draw the H on the outside. Or the bromine can end up on the outside and the H on the inside. So those are the two possible products. And from chapter 8, we know that this is the desired product or the favored product. And this was called anti-Markovnikov. Because our electrophile, which is H, that is not shown, ended up on the more substituted carbon. And normally you want your H on the less substituted carbon to leave the carbocation for your more substituted carbon. This goes through an opposite mechanism because of the peroxides. And so we didn't learn the mechanism for this problem because this deals with chapter 10. Okay. So how can you confirm the product by Proton Nmr? What key peaks would allow us to tell the difference by NMR? So in general, the H's connected to nothing special are just going to be around 1 to 2 ppm. So we want to focus on the H's connected to a heteroatom. And so we have the H here connected to the carbon that bromine is attached to, and then we have 2 here. If you look on your chemical shift chart, that H is expected from 3 to 4 ppm. So between 3 and 4 ppm, we should see 1 H here. And at 3 and 4 ppm here, we should see 2 H's for the integral because we have 2H. And so that will be the key. That alone would be enough evidence. What type of splitting pattern would we expect for this H as well? So it's next to 1, 2, 3, 4, 5. So there's 2 and 3 is 5 total. And the n+1 rule says that we're going to see a peak with 6, which is called a sextet. And here we are next to 1, 2, neighbors only. So 2 plus 1 is 3, which is a triplet. And so we would expect to see a triplet between 3 and 4 ppm worth 2 hydrogens. And over here we would see a sextet between 3 and 4 ppm worth 1 H. Okay, so that's number 2. Number 3, how would APT NMR allow us to distinguish these two possible products? Okay, so pause here. Think about that. Remember the APT NMR, if you are pointing up in the air, you are a CH or a CH3. And if you are down, you are a CH2. And quaternary carbons don't show. So how many peaks would we expect to see for APT NMR here? We would expect to see all 4 peaks. We have a CH3, a CH, and a CH3. So one CH2 would be down. Over here, we have a CH2, a CH2, a CH2, and a CH3. So we would also have 4 peaks. But now there are 3 CH2s here. And we would expect to see 3 of them down. The one furthest downfield would be the one attached to the bromine. And these would be the other CH2s that would be further upfield. Remember, upfield is to the right, downfield is to the left. And a lot of this is due to electronegativity. This is connected to an electronegative atom. All right, number 4, would MS allow you to distinguish between these two products? So pause and think about that. Okay. So remember that we can see bromine and chlorine very well by mass spec. However, both of our compounds have bromine. So both would have an M peak and an M+2 peak, where one of them would be at the mass of this molecule with bromine 79, and the other would be at the mass of the molecule adding in bromine 81. And both would have it. So this has bromine and this has bromine, so you cannot distinguish. I had mentioned though that the type of mass spec we were talking about was EI mass spec, where you bombard your compound with an electron and it forms a high energy intermediate, and that can fragment further. So in reality, this will have a different fragmentation pattern than this molecule. But we haven't learned that to that detail. So from what we know in this class, we cannot distinguish those two. Now let's try 2 that are unknowns. Okay, so we're given different information in both because I wanted you to see how to put the information together. On a test or in the inverted lecture, you don't know what combination of the data I'm going to give you. So make sure you have a good understanding of proton, carbon, IR, and mass spec going into the inverted lecture. And at least have all of your data tables available. So you'll want your proton, your carbon, you want your IR data table, and you want your mass spec data table all ready. And I will post those with the notes so you have them all together. Okay. So in this one, we have a formula, C6H14O. We have proton NMR data and carbon NMR data. So having a formula is key. And from the very first slide today, what did I say to do? Okay. I mentioned that if you don't have a formula, you need one. And if you have a formula, the first thing you want to do is find the IHD. Okay, so that is 2N plus 2, 2 times the number of carbons, plus 2, minus hydrogens, ignore oxygen, and divide by 2. So that's 12, 13, 14, minus 14 over 2, which is 0. So 0 unsaturations means no double bond, no ring. Okay. Now if we go to the proton and carbon data, we want to check that we have 14 hydrogens. So here's 12, 13, 14, and it's telling us that one is an OH peak. So right away we know one of the functional groups is OH. We only have one oxygen in the molecule, so that oxygen is only an OH. And that means we're going to have an alcohol. There's no double bonds and no rings, so there's no alkenes or anything like that. So that's our only functional group. In carbon NMR, we have 1, 2, 3, 4 peaks, yet we have 6 carbons in the molecule. So 4 peaks, 6 carbons, and that tells us that we have some type of symmetry because we're not seeing all 6 carbons as unique. Okay, and then one other thing to notice is that this one here at 73 must be the carbon that's attached to your OH to be that far downfield. All of the rest of them are in the range of normal CH, CH2s, and CH3. Remember that the most upfield one tends to be the CH3. And we have information from Proton Nmr to tell us that. So if we look at Proton Nmr, we have a peak at 0.91 worth 6H. And so the only one that's that close to 1 in both of these cases, remember that CHs in general are between 1 and 2 ppm. And so if you see 6 of them together, that is usually 2 CH3 groups. Okay, so at 0.91, we have 2 times a CH3, and they are a doublet. This is our splitting pattern. This is a singlet, and this is a singlet, and then this is a septet. And so that tells you who your neighbors are. And so these 6 H's are being split into a doublet. That means they have one neighbor. So how can 2 CH3 groups have one neighbor? They must just have one H here. Okay, and that H is splitting this into a doublet and this into a doublet, and because of the symmetry, that is 6 H's that are a doublet. And that type of group is an isopropyl group. Anytime you identify a group like this, the splitting is shared. So if these CH3s are split by this H, then this H is also split by those CH3s. And so that H is next to 3 and 3, which is 6. So because of the n+1 rule, it's 6 plus 1, which is 7, which is the septet. And you see that you have the septet right here. So we use this peak and this peak. Okay, we have our OH peak as part of our molecule 2. And then we have 2 other 6 hydrogens that are singlets. And so again, that's 2 times methyl group. So at 1.17, we have 2 times CH3, but they're both singlets. So they're next to nothing that's splitting them. Okay, whatever they're attached to has no hydrogens. Okay, so these CH3s are one of our carbon peak. These CH3s are the other carbon peak. We have a CH right here, which is this carbon peak, and then we have an OH, which is attached to a carbon. And so that one I have not drawn in yet, so let me add that. Because the OH is also a singlet, this carbon cannot have anything attached either. And so if we put this all together, we have a quaternary carbon with 3 spaces for attachments. And look, we perfectly have 1, 2, 3 attachments ready to attach on there. And so I'm just going to put that all together. I have my OH. I'm going to put this attachment over here. And then I'm going to put my CH3s at the top and the bottom. And so this looks a little weird if I just redraw it. We have this compound right here. Okay. So that's a way to put puzzle pieces together to get the compound. Again, we should probably make sure that it matches our formula. So 1, 2, 3, 4, 5, 6. We should have 14 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, our last problem puts together mass spec. Okay, so they're giving us a mass. We're getting an IR, and we're getting a C13 NMR. And I have a note here. Notice the odd molecular mass, and so 101 is an odd number, and so that means it has to contain nitrogen. Before we do the rule of 13, so as soon as you have a mass, you need a formula. And you want to do the rule of 13. However, we want to have an idea what else we might have in there. So let's look at our IR and C13. We know we have nitrogen because of the mass. If we look at IR, we see peaks out here that are in the OH region, but they're not broad enough to be OH. If you look back at an OH spectrum, they're a very broad peak out here. So when you see other types of peaks out here, remember that the only other thing that we saw out there was an alkyne. But that was at 3,300, and it was sharp. Very sharp, and that is not the case. These are still a little bit broad. So what else is broad out there were NHs. Okay, so we don't have an alkyne because an alkyne would also have to have a 2200 peak, and we have nothing in that region here. If we look down here though at 1655, this is a little low, but this is in our carbonyl region. You may say, well, that's also in the carbon-carbon double bond region, but remember that those are weak. A C double bond C has a dipole that's very weak because the carbons are essentially the same electronegativity. However, a carbonyl has a very strong dipole. And remember that the dipole resulted in intense peaks. And look how intense that peak is. It's almost to the bottom. So we have a carbonyl group. To confirm that, C13 should also show that, and we do. At 180, we have a carbonyl peak. And carbonyl peaks in this region can be an ester, they can be an amide, or they can be a carboxylic acid. Okay. Remember that if you're at 200, you're more of an aldehyde or ketone, but 180 is in this realm. And so if we look at our information, we have a nitrogen, we likely have NHs, and then we have a carbonyl. That's going to say that we're probably favored to have the amide because the amide has that carbonyl arrangement that we need. Okay, so when we do the rule of 13, we're going to add in nitrogen and we're going to add in oxygen for our amide. Okay, so for the rule of 13, pause and make sure you know how to do this first. We are going to take 101 and divide it by 13, and that's going to give us 7. So 7 is the number of carbons. Carbon contributes 7 times 12 because this is the main isotope of carbon. It contributes to that weight, 84. And so to find the remainder of that weight, we subtract 101 from 84 and we get 17. And this is the number of hydrogens. And so we have C7H17 is our formula. We want to add in nitrogen and oxygen. And so nitrogen weighs a CH2 group. So we have to subtract the CH2 and add in nitrogen. And then oxygen weighs a CH4 group and add in oxygen. And so carbon minus 2 is C5, 17 minus 6 is 11, NO. And this is our formula. Okay. Once you have a formula, you can do the IHD. And so it's 2N plus 2 minus hydrogen minus chlorine or halogen, and then plus 1 for nitrogen. Okay, so we add for nitrogen and we ignore oxygen. So that's 10, 11, 12, 13. 13 minus 11 over 2 is 2 over 2, which is just 1. So we have 1 unsaturation. And our amide must be our unsaturation. Okay, so the amide pairs perfectly well with having NHs. And remember, the number of peaks in this region told you that you had 2 NHs. If you had 1 NH, you would just have 1 peak. And so we have 2 NHs. And we have 5 carbons total, and we've used 2 of them to make our amide. And so how can we use the remaining 3 Okay, so we have 3 carbons left, and we have only 2 peaks left in our spectrum. And the carbon NMR says weak, and weak meant, what did weak mean? It meant that you had a quaternary carbon, most likely. Okay. Sometimes you have weak peaks for other reasons, but the fact that I'm telling you they're weak here means that they're quaternary carbons. And one of them we've accounted for, so we need 1 more quaternary carbon and then 3 more carbons attached to this molecule. And the only way to do that, and we must have symmetry as well, because we have less peaks than carbons. That is the only way that you can attach them all, get your quaternary carbon, and have your 3 carbons that extra to the molecule. So 1, 2, 3, 4, 5. So you have C5. There are 9 H's here, 10, 11, NO. And so this is our formula, would be this amide. Alright, so that completes the practice problems. So hopefully you will try some of the problems on sapling. At the end of chapter 9, they deal with these same type of kind of putting together a compound or from an unknown using the spectral data. And we will have some of these problems in the inverted lecture. Okay, thank you.